Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very glad to introduce Michael Vibro. He's a research fellow in the Clayton School of Information Technology at Monash University of Australia. And Michael has attracted several awards, including the Core Australasian Distinguished Doctoral Dissertation Award for the Best Computer Science Thesis of 2008. And currently, he is working on tools which provide edge routing and placement for diagramming. So I hope it will be a very interesting talk.
Thank you, Lev, and thanks for coming. So this is work that I've been doing as part of my PhD research, and directly following that over, I guess, the last sort of 5 or 6 years. It's collaborative work that was done with a few people. Tim Dwyer, who's now at Microsoft, but while he was at Monash University, as well as Kim Marriott, Linda McIver, and Peter Stuckey. So I just wanted to mention that. This talk today, I'm going to talk specifically about placement tools for diagramming, and these are things like geometric tools for layout. I'm going to talk about the way that we're advocating implementing these, which is via the use of multi-way constraints. And I'm going to present to you some results of some usability evaluations that we did comparing multi-way tools with other solutions. I'm also going to talk to you a little bit about the ways that we approach connector routing in diagrams as well. So, all right, let me start out and give you some motivation. This is an image that came from just Googling for phases of the moon. So if you type this into Google, you'll get probably a couple of hundred images that show effectively the same thing, the different phases of the moon, depending on the position of the Earth or the rotation of the Earth and the Sun. One of the things you'll notice looking at a diagram like this is that you can immediately see that there is intended layout or geometric relationships within it. Things are mostly in line with each other. Labels are mostly centered with the accompanying objects that they're labeling. But you can also see that this is something that has either been arranged by hand or with a piece of software that probably didn't provide great layout tools. And I say this because you can see the intention in the diagram, but you can also see where it fell down and the intention has not been fulfilled. And that is that certain objects are not correctly in line and certain labels are not quite aligned or centered with objects. So it's probably better to create diagrams where you fulfill all of these relationships because, one, they just look neater, but this is more important because where you have these relationships that aren't quite satisfied, it's a little jarring, and these are things that users will notice, and there will be this unintended implicature, okay, where people look and possibly see some information that is not relevant at all and shouldn't be there. So if possible, ideally, we would create tools that allow the user to fulfill these relationships as easily as possible and maintain them throughout their editing. So a few points of note. Producing well laid out diagrams is going to be difficult and tedious for users if they do it manually, okay? You're often going to want to be doing things like aligning and distributing objects spacing them equally. Now, many existing tools have automatic features for things like grouping objects together, connector tools that will automatically reroute connectors as you move objects around your diagram. But these are not a complete solution and don't satisfy the problem completely. Also, some existing software, or a lot of existing software, just provide layout tools where you select some objects and you click a button and you say, I want to align these objects. And literally all that happens is you get movement to a new position, and there's no persistent relationship at that point. When you use these and you change parts of your diagram, you're going to find that you need to repeatedly make use of these tools to keep satisfying such relationships. So you have this problem of repeated use where you're requiring users to do the same task over and over again, which is very annoying. So let's talk about some of the existing tools. The first one that many pieces of diagramming software offer are what we're going to call once-off placement tools, and these are the ones where you just have some shapes, you just select them in whatever way is necessary, and you apply a tool that moves them to a new position. And I'm sure you're all familiar with this because basically any piece of diagramming software has this ability. The key thing here is there's no lasting relationship. The next way, and this is something I'm sure you'll be familiar with as well because it's something that is offered by Microsoft Visio as part of its layout tools, is the ability to create one-way constraints, or what is intended to be a persistent form of alignment and distribution tools. And how these are actually implemented is that you have a guideline object that's added to the page that represents your alignment, and you have a set of one-way constraints, analogous to formulas in spreadsheets, where you set the position of a shape, like shape A in this example, the x position of it, to be equal to the x position of the guideline. In this case, the user can use the guideline as a handle or an object to move the entire alignment relationship. So they can click it with the mouse and drag it, and obviously, like you'd expect in a spreadsheet, the formulas flow through and the values update and your shapes move with it. Now, there are some issues with this, or at least we conjectured at the beginning of this research that there are some issues with this. If you really want to use these as your method for laying out objects within a diagram, you can have situations like this. So here's one of the basic situations where this causes problems. Okay, we have some shapes A, D, and B. The user selects shape D and A, and they create one of these persistent alignments. So they have a guideline. They have the positions of these two shapes have been constrained to that guideline. Next, they select shape D and they select shape B, and they create an alignment with the bottom of these two shapes. What actually happens at this point is, okay, the Y position of B is constrained to the guideline. The Y position of D is also constrained to the guideline. At this point, it can't be constrained to the Y position of both these guidelines at the same time. All right, so at this point, it's just constrained to the bottom one. And the user will not know this. They can't tell looking at the diagram at this point. It's only when they interact with it that they find out that this is the case. So when they drag this guideline, they find out that the relationship they set up is no longer there. So a few issues that we felt there were with doing this via the approach of one-way constraints. Firstly, it's not flexible. Yeah. Oh, I'm sorry. So the first problem is, that it's not flexible in the sense that the user can't interact with just any of the objects in the diagram. They must interact with the guideline rather than the shapes. the ordering of the way, or the order they apply the tools matters. So if they create one guideline or alignment before the other, then different things happen. And finally, they can't evaluate the state of the diagram at a particular point by looking at it. Let's say they were to open the diagram at the third stage of that example I showed. They can't tell what's going to happen next unless they either look at the formulas that are actually enforcing these relationships, or they actually move objects and see how the attachments are connected. So what we decided to do was look at implementing these placement tools via multi-way constraints. So the idea here is that you have a constraint solver, a piece of mathematical software that sits behind the diagram editor and handles these relationships. And instead you have relationships that work in both directions. And what the behaviour of this actually means to the user who's interacting with it is that they drag the guideline and the shapes move with it. They drag one of the shapes, the guideline and the other shapes move with it. They resize one of the shapes, the guideline and the shapes move with it as a result. So that's probably fine. I'll talk about the study and then I'll show you what it actually looks like. So the first user study we actually did in this area was we looked at using Microsoft Visio, and we did this because, one, it was a sort of leading tool in its class of tools. Also because it had a plug-in interface to it, which meant we could do some of this stuff. And finally, because it already provided once-off placement tools as well as one-way constraint-based placement tools. And what we did was we implemented the multi-way constraints and gave them an interface and toolbar buttons and everything, so they were very, very similar to the ones for the existing tools. And then we gave users a set of tasks that required them to create these relationships and then modify the diagrams and interact with them. And these were sort of real-world layout tasks. I'm not going to go into too much detail about this because in some sense I feel this study was flawed, so I'm not going to tell you too much about it. But basically, the only thing that we noticed that was statistically significant in the results was that the one-way tools performed worse than the others. So they were just bad. And this sort of re-encouraged initial feelings that there were severe usability problems with them. And by what I'm saying by performing worse in this case, I'm saying they performed worse in terms of taking a lot longer for people to produce the final diagram we asked them to produce, and also the number of errors of things they could not get correct in the diagram they were asked to produce. Now, actually, we feel that, the interesting thing is multi-way didn't appear to perform any faster than the other techniques, and also the once-off tools, the very, very basic ones, were just faster and less error-prone than the one-way tools in these results. Really, we didn't have a high level of confidence in the results of this, and a lot of it we actually felt were due to the ways that these tools are actually implemented in Visio, more than because of the constraints of doing it with one-way constraints as opposed to with multi-way constraints. And what I mean by this is an example of one of the issues that Visio does is if you align an object horizontally and then place it into a vertical alignment relationship, it will actually break it from the horizontal relationship, even though the shape has not moved vertically, so there's no need to break it from that relationship. And these were things that we couldn't deal with easily in the plugin interface, so we just decided that we would re-implement a prototype editor with similar functionality so we could do a true comparison. The other thing that I will note is that some of the other issues are that users pointed out, in Visio, when you create a distribution relationship, and it turns out this is still the case with at least Visio 2007, because we're having a look at it yesterday, that when you have a set of aligned objects and then you distribute them and space them equally, there is no on-screen indicator that represents this relationship has occurred other than the guidelines change from blue to purple in colour. And at this point, they behave differently to how they used to. And if you drag one of the outer ones, the distribution resizes, and you can no longer drag the internal ones. And often the users were trying to drag these, not understanding why. They couldn't work out what the relationships were on the screen. So the next stage was I wrote a prototype diagram editor, and you'll notice it looks very similar to Visio in terms of its interface. And the reason for this was that really we were trying to do a fair comparison against the existing tools that were in Visio against these sort of multi-way constraint-based approaches. So it offers the sort of standard diagram editing functionality. You've got cut, copy, and paste, and undo and redo. And then it had both multi-way and one-way versions of these tools that behaved in what we felt was the best way possible given the constraints of the underlying techniques. So I'll actually just show you what this looks like. So this is Dunnart, and obviously we can just move objects about. You can select some objects and, say, align them. And we get a guideline here that represents the alignment, and we can move any of these shapes. There's also some connector routing going on in the background, which is why things move around a bit. If we resize any of these objects, you get the relationship is still maintained. Also, there's distribution in here, and it looks a little bit like this. You can distribute some objects. You get an on-screen indicator that represents the distribution. So this is, I guess we're trying to have a visual representation of all of the underlying constraints, so you can tell what's going to happen before you even interact with it. Also, this is an object that you can use to alter or to remove the distribution relationship. So I can hit delete and remove the distribution relationship. The guidelines will remain. I can resize the distribution. In fact, I can choose to resize it around any particular guideline in here if I choose to. I can also add and remove objects to these relationships. And I can, say, delete a guideline or remove it from a distribution by dragging it out. And then this one's now free. And the rest of the distribution remains. So this next study we did, we looked at specifically the usefulness of multi-way tools versus the one-way equivalents. And as a secondary thing, as part of this study, we also considered what the value of having immediate feedback in such constraint-based tools was. And what I'm really referring to there is, you'll notice in Dunnart here, everything that you do updates live. All of the connector relationships, all of the alignment and distribution relationships, as the user interacts with them, they get immediate feedback as to what's changing. This is in contrast to what you would see in some other software, where instead you see, you click an object and you drag it and you see ghosted outlines of that object until it's placed at a position, and then any updates that happen as a result, like maybe some connector routing, happen. So we implemented both of these versions, so you can also drag these objects and then the constraints update once the user has finished their movement action. So some of the exercises were things like beautifying a diagram, which is in the sense the standard task someone might do if they were just given a diagram that's been very quickly arranged by hand, and they just want to align up objects and space them quite neatly. And this doesn't usually require much actual interaction with the constraints themselves. Like, it should be, if you do things in, say, an optimal order, you could do this with the same number of clicks or actions, regardless of whether you're using sort of one-way tools or the once-off tools or the multi-way. But then we got them to do some other exercises, which were things like saying, okay, you have this diagram arranged, you now flip it to a landscape view, and we want you to rearrange it to make use of the space on the page and make it look something like this. So what we were doing was we were giving them tasks that had real-world motivation, so they could see why they were doing it. They were also, in some sense, a realistic diagram. This is one about just making a cup of coffee. But and we also suggest or said that these are the relationships we'd like to be present in the final diagram. And we gave them a few pages of printouts that showed the initial diagram they started with, the target diagram, both with and without these indicators for the relationships shown on them. So, and then we looked at timings and error rates and things. So this is an interaction plot that shows mean times taken to finish the tasks, and also with error bars on them. So the initial things to take away from here are firstly that the blue and green line, which represent the multi-way tools, are overall faster to complete the tasks and statistically significantly faster than the one-way tools in general. So that's just that the blue and green lines and their own error bars are completely below the red and black lines. The other thing to note is the crossing here, basically where you see a crossing like this, it says to you that the tools behave differently for different tasks. So in this case, this first task was this beautify one where it didn't really require any interaction with the constraints, like actually working with them once they were created. So we ended up getting a different result, that the immediate feedback tools performed better than the delayed feedback tools in this result. What is perhaps particularly interesting here is that the delayed feedback versions were faster, and this is a trend, but it's not statistically significant, than the immediate feedback. And this is sort of against what we'd expect, because we conjectured that this immediate feedback was beneficial to the user. It should make them be able to perform the tasks faster because they see exactly what's happening immediately, and they can do things without having to wait and then ultimately go, oh, that's wrong, I'll now reset and choose to do something different. So, yeah.
Did you have easy undo?
Yes, in the sense that you can just drop something and hit undo. You can also do escape. In one of the early ones, we didn't have like hitting escape during the action, but we did later on. So, yeah, the first thing to take away from this is one-way versus multi-way constraints. Okay, it's very obvious that the multi-way constraint-based tools are faster to accomplish these tasks, and they also result in less errors. What is interesting is that for immediate feedback, we know that there's some value for comprehension involved in this. And specifically, one of the interesting things that were noticed during watching replays of this interaction is that participants will instinctively shake objects or sets of connected constrained objects. And they sort of do this as a way of going, okay, I'm just going to see how's this object relate it to other things. And they just sort of move it about a little and go, okay, that's what's going to move, and then I'll drag it somewhere else. And this is particularly interesting because this wasn't part of the training that we provided to users. We didn't say, okay, these are constraint-based tools, they update live, this is a way you might like to use to understand how they interact with each other. This is something that, because the behaviour of the tool is quite a real-world approach or sort of metaphor for them, they just make use of it and they do that automatically. The second thing that's really interesting is that, okay, the immediate feedback did not lead to significantly faster times, and this sort of comes to your question. And we went back and we looked at why this was, and it turned out that the reason it's slower is that people have this system of real-world interaction where they drag something and they go, okay, no, that's wrong. Rather than realizing they're doing something wrong and taking the easy undo approach, which is very easy, you hit escape or you drop it and you hit undo and everything jumps back to how it was, they don't do that. Instead, they manually and slowly drag objects back to where they're originally positioned, which is sort of the real world approach of how, if you were doing this with connected objects in the real world, this is what you'd do. So we found this quite interesting. We suspect, but we haven't tested it, that if you were to do training on these users and tell them that this is a much faster and easier way to do this, you'd get by without it. You'd negate the effects of this, I should say.
Another question.
Yeah.
So when they jiggle the objects,
Yeah.
did it end up slightly changing their diagram, by a pixel here, a pixel there, what I'm wondering is if you were to add a feature where if you mouse hover over something, it just automatically jiggles everything connected to it.
Sure.
If that would have helped or not.
So I think that quite possibly it would, and I'll just talk about this stuff in a second. So yeah, exactly. One of the follow-up, we did a follow-up study to this, and this was also just looking at, in a little more detail, ways that we could possibly avoid this problem of clutter, because one of the things that we noticed from the very first study we did and the later one I just talked about, one of the common criticisms that we got from users, or ways that they felt that the software could be improved, was that there were too many things shown on the screen. And this especially becomes the case when you have lots of these constraint indicators that represent guidelines or alignments and distributions. The other thing we did as part of this study was looked at ways that we could possibly help the user understand the system of constraints that were actually on the screen, and particularly how objects are connected, because one of the problems that I guess some of these users ran into would be, I set up these relationships, but then sometimes I still don't understand exactly how they interact. And they move something, and an object they don't expect to move on the screen moves with it, and they sort of go, okay, why does that happen? And it's hard for them to figure out often the chain of constraints that may cause this to occur. So some of the stuff we did here was there were a fair amount of suggestions, and these also come from some suggestions that have been made in literature on constraints in diagramming tools as well, because this is a well-known problem, this issue of clutter on the screen. We had some options where we could try doing different things, and some of these were have the indicators glow when they were active. So if you move a shape and another shape is attached to it through a guideline, you have that guideline glow orange, and it sort of highlights the effect of the movement. And the immediate feedback we think should be helpful for this, because it does motion highlighting in a sense that you see the movement of all the objects that are connected, which is, I guess, why the jiggling itself is useful. We also tried having just a constant reduced visibility to these objects, so they're just shown with some level of transparency. And also the other thing we tried was looking at having them fade out when they're inactive. So basically, rather than glowing, I guess, they would be at full visibility when they were in use, and then over, say, a couple of seconds, they would just fade down to a reduced level of visibility. And what we found, and the second thing we did as part of this tool was something similar to the jiggling you were talking about, but not quite. And this was to have a sort of query tool. And sorry about this, looks terrible, but it was with an old version that showed connector points at all times and stuff. But you select an object, and then you can use brushing to basically move your mouse cursor over other objects in the diagram and see if and how these objects are connected. So in this case, this particular shape here is connected through this guideline, which is attached to the selected shape, through this distribution to this shape, which is both center aligned and left aligned, and through here and to here. So from this study, our findings were basically that the participants preferred, their preferred, I guess, visualization for this was for the indicators to fade when inactive, but remain at full visibility when they were in use, when they were active, and to fade down to a just visible level. So really, obviously, you don't want to hide something on the screen and have it disappear completely. That's going to be terrible. Same problem we had initially where the user just can't evaluate the state and how the diagram is going to interact before they make changes to it. Also, interestingly, this took away the complaints that we had about clutter. And we used the same actual tasks, so you would expect to have got similar feedback where we got, say, feedback on this clutter issue from 60 to 70% of our initial participants. We didn't get it here. Instead, they complained about other issues instead that they felt were more problematic, or the ways the tools could be improved by automatically inferring alignment or distribution relationships for them. They sort of jump onto the next level of what's possible. The other thing that came out of this study was that this query tool of doing the highlighting as you move around was useful. It helped some participants. It still did not get rid of this issue completely. People were still left going, okay, sometimes I want some feature or tool. They weren't able to describe how they wanted it to actually react. That gave them information about how these connections operated. And no, so in answer to your initial question, we did not do something where they could, say, select an object and have the accompanying ones jiggle, but obviously it may not be required if you have immediate feedback, I guess, because the user can very quickly do that, though I guess it allows them to do it while knowing that they don't have to change the state of their diagram in any way. So it would be very easy to implement and possibly quite useful. Oh, that slide wasn't supposed to be in there. So in addition to this, we've later moved to doing some automatic layout stuff, which I'm not going to talk about today because Tim has probably already talked about quite a lot of it here, but you can approach me or him separately, I guess, if you're interested in more of it. But at the same time, we switched to using a different solver to represent these placement tools and placement constraints. And as a result, we implemented some further additions to the placement tools we had available. And some of these things were automatic non-overlap of objects. So this is basically just that. I'll just get rid of these. You can just turn on non-overlap of objects, and as I drag them around, they just run into each other and can't cross in any way. They just bump into each other and move. Also, we created a tool for allowing minimum separations to be specified between guidelines. So this is sort of similar, but not exactly like the distribution. And I'll show you how this looks. You basically select some objects and say keep them separated. And again, we get an on-screen indicator that represents this separation. You'll notice it basically glows red when one of these constraints reaches its minimum size and starts interacting. And you can see as they bump into each other, this kind of occurs. Also, you can click on the relationship, obviously remove it, but also resize this minimum separation if you desire. And delete it as well. Also, we did page containment, which can be done very easily with these same separation constraints. So objects now are placed within the page, but because you still want to allow the user to have what feels like full control over the application, you want an object that's dragged with the mouse to still follow the mouse as you move things. So you don't want to make this constraint on the page stronger than the one that holds the dragged object to the mouse cursor. So as a result, it can sort of still balloon out sometimes. So if I push an object with the one I'm holding with the mouse, it will go outside the page. But then if I let go of it, it'll spring back. Or if I just move it out of the way, you see the page spring back. And again, all of these tools we're working on, our aim with them is to take tasks that the user would usually fulfill manually or with a repeated process, and instead make the diagram editor maintain them automatically while still giving the control to the user to be able to alter these relationships and, I guess, direct how they behave. The other thing that we've really been trying to do as part of this is make sure it's very clear to the user the behavior of them based on the on-screen representation. So I guess we've worked hard on what it should look like when things like these page layout constraints are not quite satisfied, or when you actually, I guess, what different constraint relationships should look like. So I'm going to stop talking about the placement tools at this point and talk for maybe the next 10 or so minutes about connector routing that we're doing. And again, you've seen it's just going on in the background of Dunnart as I was doing this. We're using an approach for this polyline connector routing. And in fact, we're also doing this for orthogonal routing, which I'll show you in a moment, where we construct a visibility graph of which objects can see which other objects. And then we do a search through this graph and find paths. And then we do like a final stage that improves these routes where necessary. And we particularly choose this approach because it gives us a lot of flexibility, which I think is really important or beneficial in the context of a diagram editor, where if you're in a diagram editor, often the user's going to have certain diagrammatic conventions that they're following. Obviously, a lot of the time, aesthetics of the diagram are important for readability, or all of the time. So it's fine, I think, to take, say, just optimal approaches from literature for a certain problem, but then quite often I think there's a need to adapt these and give them some flexibility to make them more useful within this particular context. So the key reason we chose these is really this flexibility to capture certain diagramming, drawing conventions and aesthetics. So, like, as an example of this, I'll show you first of all, like, what is actually happening here is this is the visibility graph in this case. It's basically a graph that connects all of the corners of all of the shapes as well as the connection points. And it's not a complete graph in the sense that there's no need to have certain edges in it, like there's no need to take the bottom right corner of this shape and the top left of this one, because nothing would ever go directly from those corners. It would always, come around the shape or come from a connection point that was inside it or similar. But then when you're actually doing the determination of the paths through here, and I realize I don't have exactly the right demo, so I'll just start it up manually. Tests, path, demos. We're using an A-star approach or search through here, and we can change the cost function to add penalties to it. And as a result, we can change the properties of the routes that are produced. So one of the things is you might go, okay, I want to have penalize sharp angles within these connectors. And as you move up this penalty, you start getting sort of better routes for it. You could also just penalize strictly the number of segments in the connector. And you'll see as you raise this penalty, you start getting routes that are possibly more aesthetically pleasing to the user. One of the improvement techniques we use in these kind of cases is where there's shared paths or routes that come together, is cases like this where things go around the corners of the same shapes. You obviously want to avoid this because it's hard for the user to tell exactly which path is which, other than obviously clicking on them and seeing one selected but not the other. So we do a stage where we determine ordering of these things, and we actually nudge them apart so that there's space between them. I can't actually show you in this one, but I'll show you in the next one what this looks like. There's some issue with it right now.
You do it for non-recurrent case either.
Yeah. Well, because, and I guess I could show you some of the produced diagrams for it. Maybe after the talk, come and see me. Because, yeah, like it's quite common that you might have a couple of connectors run from here, and then they also run like together down here and apart later. And it's just really hard to follow them, right? So if you can do this, there's a couple of things you can do, right? And this is really the benefit of the approach is you can look for these crossings once you've generated all these paths, or even do this on the fly when you're first generating the paths. And as part of your cost function, you can actually look for these crossings or shared paths and penalize them depending on their actual properties. So if they run in parallel but then diverge and you know that they don't cross during the course of their shared path, it might be fine to leave the routing like that and just nudge them apart. But if they do cross, it might be that for one of them you want to try searching for a different route for it, which might be slightly longer but may have no crossings to it. And you can do this for do crossing detection for all these things while you're routing, but you take a penalty, like a speed hit for it. So the way I've actually implemented it in here, and I'd probably advocate doing it, is to do all the initial routings and then look for problem cases. So do crossing detection there once for everything. And if there's particular things that you want to fix, you do it at that stage. And ideally in an interactive context like this, the user physically just selects something they don't like and says, hey, I want to reroute this connector and I don't want the crossings, and it fixes it. So this approach also works for the orthogonal case. And this is, I guess, important here for you guys as well. I know you're working on this a bit as well. This is the orthogonal connector routing in Visio, and I'd like to point out a couple of things that are really, I feel, problems with it. First one is you get issues like these where you can't tell exactly where the paths go, so the overlap's a problem. Second is you can see some artifacts in the routes or the layout of the technique that is used to actually determine the paths here. So, and this is basically, where does this line segment end up? Does it end up against shape F, or does it end up against shape E? And this will be dependent upon probably the direction that the search is performed when looking for these routes. And the interesting thing is, as you move things about, these change. So it's not at all predictable for...
So this path was going from B to G, I believe, and hit F and turn to the right.
Yeah, and I think I agree. That's what it looks like here. But really, the issue with this is that a user who is using it shouldn't need to have any idea of what the underlying algorithm is that's being used, right? The tool should behave predictably and in the same way, regardless of, say, the direction that the routing's performed. So ideally, like, this would be centered in this space, and likewise for the line up here. And we do something about this. So this is all stuff that we can do by using these kind of approaches that I talk about. So this is with rounded corners, but it doesn't have to have rounded corners. It looks a little strange. So this is what the same diagram looks like in Dunnart. Here's the visibility graph that it's routing through. And I can show you what the sort of interaction looks like as you move things around. And you can see this segment here is centered between these objects, and you can see the sort of behavior as you move things around. The top bordering here is a bug. I don't know what's going on there. I was working on an optimization for this that may have broken some things. Also, the case I haven't implemented is the one where you just block the visibility because, let me see if I can do this somewhere like here. This is just where it doesn't have a line of visibility anywhere because these shapes are actually overlapping. Something smarter needs to be done here. And this is actually because there's a port on the top of this shape. So it's not that this shape has visibility in all directions, which ideally, if it does, like these sort of cases don't really occur. I mean, we could actually do that here, I guess. If you connect to the center of this shape, and maybe I should point out the other part about this is how we handle connection to like the center of shapes here is you actually just have a point of visibility and special edges within the visibility graph that just give you connection to the ports on the side of a shape, and it will automatically just determine the closest one based on that search anyway. So there's no extra sort of logic that's required in your algorithm as part of this. So there's a few tricky things that are done as part of the improvement step of this. The first one is you need to do this sort of detection of things like crossings and ordering.
Can you define a port which is not a point?
Can you, sorry?
Can you define a port like anywhere on the top?
Yeah. So of a shape. Yeah, the ones in Dunnart right now have fixed ports on the middle of each side of the shape, but there's no reason you can't place a port anywhere. If you come and see me over after the talk, this actual research is being funded by an industry collaborator who's actually interested in this for circuit diagram layout, and quite obviously their objects are like integrated circuits with pins all along the sides of them, and one object might have 20 connections or whatever. So yes, it certainly works. Effectively, all you're doing is you're just placing a point that you're giving visibility in a certain direction, and sometimes it has visibility through the edge of a shape if it's contained within that shape. The other nice thing about it is we do this nudging step, right, that nudges apart these shared paths, and in fact does it when they flow through multiple segments. And what that actually is doing is it's firstly determining an ordering for these things that prevents them from crossing or makes them just cross once if there is a crossing that cannot be avoided. And then it's determining the area of free space it has in the dimension that it's doing the nudging. And if you would like your ports, so in this case, we have two connectors that are going to the same port on a shape, but there's absolutely nothing from stopping you from doing the nudging for those final segments. So in this case, because our channel of free space is here, we would actually nudge just in the line of visibility and up to the edge of the shape there, and the nudging would just space them out equally along that shape from their center. So effectively you get sort of a nice space layout in that case for free, without doing any extra work. Okay, so I'm not going to go into any more detail for that because I guess my hour here is about up, so I will conclude, but you're welcome to come and talk to me and I can show you further demos of these things or explain to you exactly what's being done in the background. So the key thing I guess I really want you to take away from the talk is that we can certainly provide both layout tools and connectors that automatically maintain, say, drawing styles and features, also that allow the user to customize the layout, and that also save the user a lot of effort. Okay, so a lot of these things can be done automatically, but they can be done in a way that's a way that is done well and is predictable for the user, but also gives them flexibility. I think it's really important to make these things behave not truly optimal, but in a way that the user can understand and work with easily. And I also think that the interface for a lot of these tools is really important. And I think that these are points that are often forgotten. So at that point, I'll say, if you're interested in further information on like these user studies or the research, there's my website, which is here at Monash at the top. All of the underlying methods we're using for doing both the connector routing and for doing the constraint solving and things are part of a set of C++ class libraries in the Adaptograms project. And my prototype editor is also available as some binary downloads at the moment, but the source will be available sometime shortly as well. And I will say thank you for your attention.
Questions?
I guess we have them in the middle.
So what I find very interesting here, Michael mentioned a company that subsidizes his research. So they don't keep the results of the work private. So they still can publish. Michael can publish.
It's open source as well.
So the interesting thing is they basically came to me and they said, we've seen you've done this polyline connector routing, and I said yes, and they said, we also see that you say that you're planning to do this orthogonal version. Have you done it yet? And I said no. And they said, could you do it quickly? We have a release coming up in 4 months or something. We're interested in this. And I said, yeah, it'd probably take a couple of months of work to do an initial version. It won't be great, but we can investigate how to optimize it later. And they said, okay, so how much will it cost us kind of thing? And we said, these are what we'd like. We'd like for the university to own the intellectual property. And the weird thing is the library was already open source. It was already OpenGL. They could already have used it, but they preferred to pay us an additional licensing fee and get the rights to basically use it without telling anyone they were using it and to not follow the license restrictions, which is not providing source code for the library and not providing basically dynamic linking of the library.
So you dual license?
Yeah, so, and that was okay because the only authors of it are myself and Monash. So, yeah, so it's dual licensed. But they are completely happy for the work to be published, which is why I'm actually here, because I was in Chicago last week presenting the orthogonal connector work. And also, yeah, the implementation is all open source. And in fact, the implementation of the orthogonal connector routing has just been put into Inkscape as well, the open source vector graphics editor that sort of competes with Adobe Illustrator. So that's going to have some orthogonal diagramming capabilities. So I was mentoring a summer of code student over the last couple of months doing this.
I think it's great work. So you have this leave avoid.
Yeah.
That shouldn't be avoided.
Yeah, that's right.
So you mentioned for the ports,
Yeah.
you want to provide a port which is only the top.
Yeah.
You provide several points of connection. You don't provide the entire surface.
No, so in fact, all I'm doing so you could, okay, if you're worried that you won't have like visibility to the center initially, you could certainly do this. At the moment, all I'm doing is I'm just providing a single port, and if I want to space things out along an edge of a shape, or I just do it at the improvement step when I do this nudging, which is I've got a path that I know goes through there. I've got some free space that I can easily determine, and how I do this is I sweep through the diagram and look for these channels. So I know where the obstacles are and how much space I have to the edge of the shape. And then I know also the ordering that is required to prevent crossings. And then at that point, I just space them out. But if you were worried that you may not have visibility to the center, you could certainly provide, like, I don't know, 3 of these, but you don't need very many, like equally spaced along there or something. I don't think there's a need to have 20 of them at close intervals and do it at the routing stage. It's going to be a lot more costly at that point to try and work out where the crossings are and where the ordering needs to be to avoid the crossings. So the code that's used for doing this, that's used to do the ordering, is basically similar to the approaches that are used for determining like metro line crossings.
We need to
Okay.
close the talk and then
Sure.
we can discuss it. So
Okay.
let's thank you.